The Unseen Engine, Mastering Custom CUDA at the Edge of Computing. This video explains why the fastest AI systems do not stop at model.to CUDA. They descend to the silicon, kernels, memory hierarchy, and hardware-aware optimization. Theory today, live kernel coding in a follow-up. The high-stakes frontier of optimization. Kernel engineers at xAI-scale language models beyond 1 million tokens with custom tiling, 2 to 3x speedups, translating to millions in saved compute. Edge robotics engineers hit sub-10 millisecond vision on power-constrained GPUs using int8 quantization. Algorithms researchers build breakthroughs like FlashAttention with novel unsupported math operations. 3 roles, 1 skill, speak the language of the chip. The illusion of framework magic. Model.to CUDA looks like one line. The reality underneath is generic kernels, blocked data flows, constrained memory bandwidth at 65% utilization, thermal throttling, and critical latency. PyTorch and JAX brilliantly abstract the GPU, but on novel H100 or B200 architectures at extreme scale, default abstractions become your primary bottleneck. The threshold for custom silicon. PyTorch defaults use standard models, standard batch sizes, and optimize for development speed. Custom CUDA enters when you need novel unsupported operations like FlashAttention, unprecedented scale with 1 million plus context, or 240 FPS embedded inference, or extreme edge latency under 10 milliseconds with hard power limits. Architecture, scale, and constraints, not ego, trigger the descent. The accessible frontier. You do not need decades of GPU experience to beat PyTorch baselines. Early journey engineers routinely outperform defaults on specific GPUs with hours of systematic hand optimization. Kernel bench data shows frontier LLMs, given step-by-step documentation, can independently write custom kernels and sweep configurations past off-the-shelf implementations. The curve dips before it rockets, persistence pays. The architecture divide. The host CPU is the project manager. Few powerful cores, massive caches, thread-level parallelism, latency under 10 nanoseconds. The device GPU is the factory floor. Thousands of simple ALUs, data-level parallelism, bandwidth over 1 terabyte per second. An RTX 4090 packs over 16,000 CUDA cores. Sequential logic lives on CPU, matrix floods live on GPU. 2 worlds coordinating through PCIe or NVLink. The Dataflow ping-pong. Step 1, allocate VRAM on the device. Step 2, copy data from host RAM to device VRAM. Step 3, execute the kernel in parallel. Step 4, copy results back to host RAM. Every training step ping-pongs across the bridge. Custom kernel engineers obsess over minimizing trips. Fusion exists partly to reduce this tax. The SIMT execution map. You write for one thread, IX equals thread IX.x, add of IX to be of IX. CUDA launches thousands of parallel copies. Single instruction, multiple thread. Every worker runs the same instruction, but individual threads can branch and diverge transparently. Describe one worker. The hardware scales to the factory floor. Element-wise parallelism. Modern AI is matrix operations. Applying ReLU to 1 million values is not a loop of 1 million sequential steps. It is 1 million simultaneous threads, each computing max of 0 and x. Every element processed in a single stroke. That is why GPUs and deep learning are a structural match, not an accident. Recognizing anti-patterns when parallelism breaks down. Dense predictable compute shows straight synchronized lanes. Warp divergence and latency walls show jagged crossing paths hitting brick barriers. 3 killers. Small-scale problems where PCIe overhead exceeds compute benefit on a 10 by 10 matrix. Low arithmetic intensity, where the GPU starves waiting for data. and irregular workloads with unpredictable branching that neutralizes SIMT advantages. The true bottleneck, memory hierarchy. Global HBM spans 8 to 80 gigabytes at 2 to 3 terabytes per second, but sits 200 cycles away. L2 cache holds roughly 50 megabytes. Shared memory and L1 deliver 10 terabytes per second at 30 to 40 cycles. Registers sit 1 cycle away with under 255 per thread. The rule: the fastest algorithm has the most GPU-friendly memory access pattern, not the fewest operations. 5 layers of acceleration compound. Level 1, naive kernels, often slower than PyTorch. Level 2, memory optimization, coalescing and shared memory. Level 3, tensor cores for order-of-magnitude matrix multiply jumps. Level 4, kernel fusion keeping data on chip. Level 5, quantization compressing numerical precision. Each layer multiplies the previous, not adds. Bypassing the bottleneck with kernel fusion. Sequential matrix multiply, then softmax forces intermediate results to slow global memory. Orange zigzag paths up and down the funnel. Fused kernels keep data in shared memory and registers, green loops at the bottom. FlashAttention is exactly this. One kernel, ultra-fast memory, massive sequence lengths unlocked by cutting bandwidth overhead. Extreme compression through quantization. 32-bit floats shrink to int8, int4, or lower. BitNet research runs at 1.58 bits per weight. Roughly 20x compression lets powerful models run on edge hardware or fit entirely in a single data center GPU's VRAM. Precision is a dial, not a religion. The compounding multiplier effect. Memory tiling times kernel fusion times hardware utilization times quantization equals superhuman performance. Optimization techniques multiply, they do not add. xAI-scale millions in savings came from keeping data at the bottom of the memory funnel, leveraging specialized silicon, and shrinking the footprint. A massive gray PyTorch cube compresses into a dense glowing custom CUDA cube. Tangible impact on the silicon floor. Throughput, 350% faster token generation. Latency, sub 10 millisecond time to first token for edge robotics. Memory, 1 million plus token context on existing hardware. Training cost, roughly 70% budget savings on GPU clusters. Understanding the machine at its fundamental level produces better models and better solutions. The frontier belongs to those who control the silicon. That is the silicon frontier in theory. CPU versus GPU, SIMT, memory hierarchy fusion, and quantization. In the next video, I will write and profile custom CUDA kernels live. This episode stayed architectural on purpose. Subscribe to Life of Geeks, comment CUDA for updates, and scan the QR code for the channel.